Hello, everybody. We are back with another visual pattern challenge. Here's the visual pattern. Here's step one. Here's step two. Here's step three. And your challenge is to predict how many of these O's are going to be in step four. And then if you can do that, try how many are in step 43, a little more difficult. And along the way, can you write an equation that could be used to predict the number of O's in any step of this pattern at all? So that's the challenge. If you'd like to accept it, pause the video and give it a shot. All right, so this is interesting to me. At first glance, I'm thinking it must have something to do with x squared because these are big squares, although the insides are missing, right? So we have a 3 by 3 square with the middle one missing. Here's a 5 by 5 square, but with all the insides missing. And here is that 7? Yeah, 7 by 7 square with all the insides missing. So I guess the question I have in my head is this really going to be a quadratic pattern? Is it going to have an x squared in it? Or is the frame of a square growing at a linear rate? And I don't know the answer to that right off the top of my head. But we can figure it out. We can analyze the numbers. First of all, I think just visually, we should be able to predict step four pretty easily. So we've got a 3 by 3, a 5 by 5, and then a 7 by 7. So the next one should be 9 on a side, right? And so there are 9 O's in this side and 9 O's in this side of the square. And then you'll notice on the top, it's always 2 less because you've counted the corner pieces already, right? So there'd be 7 here and 7 here. Did that make sense? So if I have a 3 by 3, a 3 side and a 3 side, then the remaining O's here are 2 less than that, all right, on the top and the bottom because we've already counted the 2 on either end. Okay, so this should be 9, 9, 7, and 7. So 9 plus 9 is 18, and 7 plus 7 is 14. And so that should be 32 O's in step four. Okay, we'll double check that when we figure out an equation, but I think we're going to have 32 O's in step four. All right, what I want to do next is just analyze the numbers because there's a surefire way to test whether this is a quadratic pattern or whether it's maybe a linear pattern, something simple. Simpler. So we're going to take the step number and then just count the number of O's. So in step number one, we have 3 and 3 is 6, 7, 8. In step number two, we've got 5 and 5 is 10, and 3 and 3 is 6, so 16. In step number three, I've got 9 and 9 is 18, and 7 and 7 is 14, and then 5 and 5 is 10, so that's 24. Okay, and we're predicting in step four that we'd get 32. So what we're going to do next is we're going to take the differences. So that's an 8. So 16 minus 8 is 8. 24 minus 16, that's also 8. And 32 minus 24, also 8. Aha. So when we took the differences, we got a constant. This difference stays the same from step to step. That means it is linear and not quadratic. So we can use the equation of a line, y equals mx plus b, to model this pattern. That 8 is what goes in for m. M would be the slope in this formula if you're graphing a line. For us, it's the rate of change of O's in this pattern. So 8 is our rate of change. It goes up by 8 every step. X is our step number. And then we would use this B to adjust it if the numbers didn't come out right. But I think B is going to be 0 in this case because look, if I have y equals 8x or 8 times step 1, that would be 8 times 1, that's 8. That's how many there are. And y equals 8 times step 2 here would be 16. So that is working out. So I think our equation is just that simple. It's y equals 8 times x. All right, now we can use that to predict the number in step 43. So y equals 8 times 43. So whatever that is, let's see, 8 times 40 would be 320. And 8 times 3 would be 24. So it looks like 344 O's in step 43. That's pretty big, but it wasn't a quadratic pattern like maybe at first glance it looked like. The frame, the outside edge of a square grows at a linear rate. Well, how did you do on that one? Did you get 32? Did you get 344? Let me know. Thanks, everybody.